Hello everyone, I am Rajiv Ranjan. I will be hosting today's session. Today is week 4 live interaction session on field structure in geology. So we have learned, so we have been through the week 1, week 2, week 3 live sessions where we have seen the introduction, and then we have learned about primary and secondary structures. Week 3 we have seen the ductile deformation, post and overprinting relationships, and in week 4 today we will be seeing some brittle deformations, strain measurement, regional deformations, etc. So the week 4 summary, if you have been through the lectures, is slicken lines, and we'll go through slicken sides. We'll also see the brittle shear zone, and you have learned joints and shear fractures followed by conjugate joints, and then we also saw overprinting relations, bearing planes, veins, and conjugate joints. And then you learn the techniques, uh, how to measure strains, shear sense, and then we saw some shear sense indicators, strain analysis, and finally we saw some 3D strain, how to observe 3D strain and how to understand, and where we saw that Flint diagram is the best way to understand 3D strain. So today we will be solving some of the problems related to the week 4 theories. And if you have in the meanwhile or during the sessions, if you have any questions, you can feel free to raise your hand, ask your questions, or unmute yourself and directly ask the questions. You can put your question in the chat box as well. Okay, so with this we will start today's sessions. So question number 1 is, identify the type of fault in the given figure. The first is reverse fault, second is strike slip fault, and third is normal fault, and the option 4 is thirst fault. So what do you think, what is the correct options? So here we can see that here we can see that, so this is the block, this is the football, and this is the hanging wall, right? So we can see, if you observe carefully, this is the slicken lines. This is giving you the movement, the direction. So we know it has slipped along this way. And if you see carefully that the thrust fault or strike slip fault, the first we can simply negate this, that this is not a strike slip fault, otherwise the movement would have been along the strike, right? So this option is negative, so this is not the correct option. Let's move to the reverse fault. Reverse fault, we know that in reverse fault, this hanging wall moves on the top of this football. This is also not correct. And the thrust fault, we don't have, this much deep angle. So we know in normal fault, according to the Anderson's theory, we know that in normal fault, we know that according to Anderson's theory, we know what, in normal fault the dip amount is 60 degree. In Straxley fault, the dip amount is almost 30 degree. In sorry, this is 90 degree, right? And in case of reverse fault or thrust fault, it's around close to 30 degree. So here we can see this is almost around 60 degree. So this is the normal fault we can identify, right? Let's move to the next question. So this is a question about the best developed lineation and foliation traces in a S-tectonite will be observed on a plane. So it's saying that where can you observe which section, about if you have both lineation and foliation traces, which we call it LS tectonite. So L for lineation and S for foliations, right? So let's try to see the options. So option number 1 is parallel to the lineation and foliation. Option 2, perpendicular to the lineation and foliation. Options 3, perpendicular to the foliation but parallel to the lineation. Option 4, perpendicular to the lineation but parallel to the foliation. So we know to best study structural or traces in a block, so we always try to observe XZ section, or you can see, right, XZ section or XZ profile, XZ cross section. So suppose you have a block, so XZ section is what? So X is the so if you have a block, suppose, okay, I will start from initials. So suppose this is an ellipse, this is a initial circular marker that's got sheared. Now it has become, so this is the maximum stretching direction and this is the maximum compression direction. So this is the shearing. So this is a case of dextral shearing. So here this is the this is X, this is Z, this is Z, right? So this is the cross section where we observe the maximum structures that forms that develops during the deformations, and Z section is the right. So suppose this is X, this is Y, this is Z, and so you have to always look in the X section. So we can see from here, so if you see here, so this is the X, so X is what? So X gives us the, so XZ is the parallel section. So if you have a, now look at a cross section of a rock block. So you have lineations like this, and you have bed, you have a bedding. So one bed, green color bed, then you have white, again you have green, and again you have white, and this shows the foliation plane. So if you have to observe, so this is the x, this is z, and this is y. So you have to always look XZ section. Remember this XZ plane, XZ section, to observe my maximum structures. So here, if you see XZ section, so XZ section means what? So if you try to cut XZ section, for example, let me take this. So it will be what? If you try to see XZ section, so this is your, so this will be your, I'm just drawing, so this will be your XZ section, right? So this is what? This is parallel to the lineations, right? And perpendicular to the foliations, right? So if you see parallel to the lineation and foliation, this is wrong. This is not both parallel to the lineation and parallel to the foliation. This is perpendicular to the lineation and foliation. This is also not right. Perpendicular to the foliation, we can see that foliation is this, and we have perpendicular, and parallel to the lineation, we can see this is a parallel to the lineation. So option 3 is correct, and option 4 is perpendicular to the lineation. We do not have such sections, right? We do not. So this is option C is correct, right? Okay, now let us try to see the shear sense indicators, or the Porphyro class, types of Porphyro class. So match the type of mantled Porphyro class in group 1 with the corresponding figure in group 2. So this is sigma type, this is delta, this is sigma type, this is phi type, and this is phi. So try to match with this corresponding figures. Try doing it, you will understand. So if you see, from the figure you can understand. So this is a, so if you have been through the lectures, or if you have basic understanding of shear indicators, or how does it forms in the during the deformations, you understand that this is very initial stage when it forms this shadows, or we have the class inside profile class, and then we have this shadow zone, and this is a phi type, and this is second. So R1 is to P3. So sigma, you can see it's very similar, you can understand from the notation as well. So this is a sigma type, you can see this is going upward, and the remaining one is, sorry, this is a delta type, and this is a sigma type. So P3, Q4, R1, S2. So option number 2 is correct. I hope you understand this. So these are important for why, not all of them, but if you see, this gives you the sense of shear. This will not, this will also not, but this too will give a sense of shear, whether it's dextral or sinistral. And you will learn in the later questions as well how does this forms. So next question is, horizontal slickened sides are observed on a surface of a vertical fault. So you know slickened sides and slickened lines. So what is the type of fault? So try to understand the question and then try to answer it. So you have a horizontal silicon sites. So if you see, just we'll try to go through one by one, and then we'll understand which one is the more correct. Hmm. Okay. Okay. So if you draw a normal fault, so we know this is simply we can understand right from very basics. You don't have to do all these things. Forgive my terrible drawings. So you don't have to do all these things. So you can see this is not a vertical fault, right? This is not a vertical fault. So the moment it says it's a vertical fault, normal fault is not a vertical fault. Oblique fault is not a vertical fault. Reverse fault is also not a vertical fault. So a vertical fault is only strict slip fault, right? So this is, so there is another block which has been, right. So we can see this is a vertical fault, and the silicon line will form will be horizontal, right? This. So Straxial fault is the correct option. So if you see normal fault, we do not have this vertical. We have at 60 degree around. Oblique fault and reverse fault is not a vertical fault, right? Reverse fault is around 30 degree. So option B is correct. We can only observe in Straxial fault. Which of the following is not found in a brittle shear zone? What do you think? Option A, myelinite. Option B, cataclasites. Option C, flow structures. Option D or option 4, pseudotactylite. So it says not found in a brittle shear zone. What do you think? Think you will get it. So we know cataclasites found in brittle shear zone, right? Pseudotactylite we know during earthquake is formed, so it's part of this brittle shear zone. Flow structures. Do you know what is flow structures? No? Think. Myelinate, you know myelinate, where does myelinate forms? It's a part of ductile shear zone, right? This much though everybody knows, right? So myelinite is a very highly sheared rock, and that forms, and that is a result of plastic deformations. So this is a part of ductile shear zone. That is why option A is correct. Hmm. Let's move to the next one. So here we have just I have kept photos. So you can see here myelinate is forming in plastic shear zone, and it's forming at deeper depths, right? And these cataclastic rocks are in this brittle domain, right? Cohesive and incohesive fault rocks. Even I have just kept here to understand these myelinites, yeah, pseudotactylites is forming in this brittle domain. cataclysite, undeformed parent rock, and then we have wide ductile shears also. So that is why option B. So you can understand from here that from 0 to up to 10 or few millimeters we have brittle deformation. And then after around 15 kilometers we have the transition happens, you know, from brittle to ductile. So we have this zone 10 to 15 kilometers of brittle ductile transition zone. So we can here see these myelinites. Okay, so next question is, if dip of the fault plane is 30 degree, then the head will be, so this is the question. So if the dip of the fault is 30 degree, then the head will be, think. So do you know like what head is? We all know dip is, right? So the dip amount is what? Amount of angle that makes with this, the fault plane or any plane makes with this horizontal. So this is, if this is the horizontal plane, so this angle is the dip amount. So suppose this is 30 degree, that's what the question says, right? So in that case this will be somewhat like this. Right, this is 30 degree. So this is 30 degree. The what head is, the head is that what angle it makes, the fault plane makes with this. So in simple way, if I try to help you understand, it's 90 minus dip, that is the head. And what is this head? Now from here you can understand. So this will be the head, right? This would be the head. And what that head is, what it makes with this. So this is 30. So to understand, you have just kept here, huh? See, so this is the fault plane, right? And we know from the horizontal what it makes is the dip amount. So here we have this alternate angle, so this also will be equal to the dip. So the head is what? The remaining, the 90 minus this dip. So what will be the value? This will be the head value, right? So here what will be the values? So this is 30. So if you try to do a perpendicular, so this would be your head value. So here what? 90 minus 30 is 60 degree. Okay, next question. Chocolate tablet structure is a variety of dash. Option A, boudinage. Option B, ductile shear. Option C, primary sedimentary structures. Option 4, fold interference pattern. What do you think? It is a part of deformation, so definitely it is not going to be primary sedimentary structure. It is no. So chocolate tablet, that says that it is going to be something like chocolate. So from here you can understand that it is not a ductile deformation, it is not a fold interference, it is a boudinage. So I will just give you an example. Okay, I have forgot, I guess I wanted to put one image of this chocolate tablet. So this is how it looks. So this is it's a type of boudinage, huh? Remember this, chocolate tablet structure is a type of boudinage. Okay, The next question is, in two dimensions, the widening direction of a tensile fracture will always be option A, parallel to the maximum compression direction, option B, perpendicular to the maximum compression direction, option C, parallel to intermediate compression direction, option D, perpendicular to the minimum compression direction. So if you know how tensile fractures forms, so for that I have just kept one image to help you understand. So suppose this is the compressive direction and this is the extensive direction. So this is the stress condition. And from here, this is how a tensile fracture is forming. Can you see? And we know the tensile fracture, how does it forms? It always forms perpendicular. So if you have, suppose you have a chalk, and this is the direction of sigma 1, maximum compressive direction, and this is the sigma 3. So we know that the tensile fracture, how does it form? It is formed something like this, right? So how is this? This is the so if you try to observe, so this is how it will form. So the widening of tensile fracture is, so widening is what? So widening is here is this, right? If you try to zoom it, so this is the widening direction, right? Because this is the minimum extensive direction, right? So what is the direction? This is perpendicular to the maximum and parallel to the minimum compressive direction. So what option is parallel to the maximum compressive direction? Option it's wrong. Perpendicular to the maximum compressive direction, parallel to the intermediate is wrong, perpendicular to the minimum compressive, it's wrong. So option B is correct, right? And that is what here we can see that this is happening, the widening is happening, this widening is happening what? Perpendicular to this maximum compressive direction. And extensile shear fracture, we know it forms around 30 to 45 degree, and this is it's an extensive shear fracture, and this is shear fracture, this is only an option. Okay, what is the condition of formation of a strike slip fault? Option A, sigma 1 is vertical, sigma 2 is horizontal. Option B, sigma 3 is vertical, sigma 2 is horizontal. Option C, sigma 2 is vertical, sigma 1 is horizontal. Option D, sigma 2 is horizontal. Tell me. Think. If you think a little bit, you will get the answer. So first try to, so this sort of question, it always in structural geology, it always good to draw, to if you are not able to visualize. So try to draw a strike slip fault. I am not good at drawing, but still I will try for you all. So this is a see, I told you I am terrible at drawing. So this will be like this. I will just give this a translation little bit. So this much displacement has happened. So this much displacement has taken place. So here what is the direction? If you try to see the strike slip fault, so this is the strike slip fault, right? This vertical fault. So if I just draw a cross section, this will be, this will be more vertical, right? So this is the fault surface. So if you try to see the direction, we can hear from here, we can understand this maximum is horizontal, right? So this is along this direction is the maximum, sigma 1, and the minimum should also be in this direction, otherwise it is not possible, right? So how it will be sigma 2 and sigma 3, try to see. Try to understand. So if you see this direction and of course the top part, so this is sigma 1, and if it is moving in this direction, it's moving, right? So the minimum is and also in that direction. So so this will be sigma 2 and this will be sigma 3, right? So if you try to see here, so sigma 1 is vertical, it's incorrect. Sigma 3 is vertical, it's not correct. Sigma 1 and sigma 3 needs to be horizontal. Sigma 2 is vertical and sigma 1 is horizontal. This is the correct rule. Sigma 2 is horizontal and sigma 3 is horizontal. This is incorrect. So option 2 is option 3 is correct. Okay, let's move to the next question. Okay, I have kept here one for this as well. So here we can see that it's a sigma 1, sigma 2 and sigma 3. That will help us to form the strike slip fault. Okay, let's move to the next question. So this is a what is the primary mechanisms of deformation in brittle shear zone? What do you think? What is the primary mechanisms in a brittle shear zones? Option A, ductile flow. Option B, fracturing and faulting. Option C, plastic deformation. Option D, folding. So we know ductile flow is a part of ductile or a permanent failure. I won't say this is the best way to explain it. So it's type of a flow, and in a brittle shear zone nothing flows, it only fractures, it breaks, right? So plastic deformation is part of a brittle shear ductile shear zone. Folding is also part of the ductile shear zone. So remaining is fracturing and folding. We know that brittle shear zone is mostly dominated with brittle deformation structure. So that is one of them is fracturing and folding. So option B is correct. Next question is brittle shear zone are typically found at what depth range in the Earth's crust? Option is 0 to 5, 5 to 10, 10 to 20, 20 to 30. I just saw you a couple of slides back the diagram where you saw the depth-wise distribution of different shear zone, brittle, ductile transition zone. So we saw that the initial shallow crustal area 0.5, so 0 to 10 is part of brittle shear zone, and typically if it asking typically, so 0 to 5 kilometer would be the correct option. So these are part of ductile shear zone. So 0 to 5 or 10, 7, 8, 10 is a brittle shear zone. 10 to 15, that's what we saw, is a brittle ductile transition, and 15 to 30 is ductile shear zone, right? So option A is correct. Which of the following feature is commonly associated with brittle shear zones? Again, the same sort of question is coming. What do you think? So we know, we learned, again some sort of question is coming. This is a part of shear ductile shear zone, right? This will also is a metamorphic ductile. This is something we know it forms in the shallow crustal condition, and that is related to the brittle shear zone. And this is also a ductile part. So option C is correct. Okay, next question is the presence of which mineral group significantly reduces or influences the frictional strength of the fault zones? Option A feldspar, option B quartz, option C phyllosilicates, option D carbonates. What do you think? Here, feldspar, quartz, and carbonates are generally are of framework mineral, right? However, this phyllosilicates has sheet structures, sheet silicates. So what this does, this significantly reduces the frictional strength. What this does is it weakens, or not, I would say not weakens it, or in one way it forms. So we know it has a layered structures, right? This sheet structure means has a layered structure. So this allows easy sliding, and which influences the frictional properties. So option C is correct. Which condition is most likely to promote the transition from brittle to ductile behavior in shear zones? Option A decreasing temperature and pressure, option B increasing temperature and pressure, option C constant temperature and varying pressure, option D rapid unloading of stress. So what do you think? So where does this transition, how does this transition happen from brittle to ductile? We saw in shear zones, right? So as we go deeper, right, after 15 kilometer or 10 to 15 kilometer, this transition occurs, right? So we can see with depth the pressure and temperature will increases, right? So we know at so this is a depth, hmm? So 10 to 15 kilometers, so with depth both pressure and temperature will increase, right? So this leads or initiates the brittle to ductile transition. Right. Okay. Next question is, what are the silicon lines primarily used to indicate on a fault surface? So what is the use of silicon lines? Option A, mineral composition of the fault. Option B, the direction of shear movement. Option C, the age of the fault. Option D, the type of the rock formation. So we know silicon lines are formed when the rocks slides, or the one block slides over the another. So it's nothing will indicate about the mineral composition, it relates the direction of the shear movement. So we saw in normal fault we get silicon lines on this fault plane. In strike slip fault we get horizontal silicon lines. This is nothing to do with age of the fault, nothing to do with type of, or the type of rock formation. So option B is correct. Which of the following ways describes silicon sites? Rough surface formed by erosion? No. Smoothly polished surface caused by frictional movement along a fault? Correct. Cracks that form due to thermal expansion? No. Deposits of mineral formed during sedimentations? No. So we know when faults move, when the fault forms, it creates very smooth polish, and along that surface, on that surface, silicon lines forms. Okay, so next question is, what geological process contributes to the formation of silicon fibers on the silicon sites? So here it's about silicon fibers. Hmm. So what happens? Erosion is not. So what is silicon fibers? So what happens if you? Okay, so I will again draw a normal fault. Hmm. Hmm. So in these surfaces, you have, you know, these are the silicon lines. Hmm. So what happens that with time, this this silicon lines gets filled, uh, due to the fluid movement along this fault plane, and then this fluid gets trapped in the silicon lines, and later this fluid precipitates, and this leads to the formation of silicon fibers. So it is the result of mineral growth. Remember this. It's not related to weathering, it's not related to sedimentation, it is not related to erosion of surrounding rocks. It's due to the mineral growth. I hope you all are getting this. Okay, next question. In which type of geological setting are you most likely to find well developed silicon lines and silicon sites? So where is the more probability of finding a better rocks, silicon lines and silicon sites? Option A, sedimentary basins with minimum tectonic activity. Option B, areas with active seismic faults and shear zones. Option C, regions dominated by volcanic activity. Option D, plains with uniform sediment depositions. Think. So if you don't have any tectonic, so you have to understand here that how these lichen lines, I have continuously speaking how these lichen lines form. So we know that this forms in a on a fault plane. So if you don't have any tectonic activities, how will you get this fault? You will not, right? So we need tectonically active regions. These volcanic activities will not help you to form, because this is not that this volcanic activities does not causes such, fault movement or brittle deformations. We need brittle deformations, right? So option A is incorrect. So areas with active seismic faults, this seismic faults is very important, and shear zones. Regions with dominant volcanic, this is not correct. Plains with uniform sediment deposition, this will not, right? This is very very low energy environment, and there will not have any tectonic activity. So this therefore there will not be any faulting or brittle deformation. So option B is correct option. So areas it requires, tectonically active regions, and so this is the active seismic faults. So when the blocks move, we know the formation of silicon lines and silicon sides happen. Okay, what is the typical dihedral angle range between conjugate joint sets? So this question is asking that sorry. So what is the typical dihedral angle range between conjugate joint sets? So if you have a conjugate joint sets, this is a conjugate shear fracture. And you can also have this conjugate joint sets. So what do you think? What would be the typical dihedral angle? So think you will get the answer. It's very simple. I saw you before as well. have you seen these structures? If you remember, so here what happens is this blocks moves a little bit, right? Because of this stress conditions. Hmm. So if you try to see what is this angle, the dihedral angle. Hmm. This is, we can see here that this is from 30 to 60 degree, right? If you try to divide these angles, this will be between 30 to 60 degree. Right. Okay, let's move to the next question. Which of the following statements correctly describes the relationship between conjugate joints and stress field? Option A, conjugate joints form simultaneously under a uniform stress field. Option B, conjugate joints can form at different times in response to varying stress fields. Option C, conjugate joints are always shear fractures. Option D, conjugate joints do not relate to the orientation of principal stresses. What do you think? So option A is it is asking about the relationship between conjugate joints and stress field. How is the stress field and the conjugate stress? So option A is saying that conjugate joints form simultaneously under a uniform stress field. In a uniform stress field, it is not possible to form a conjugate joints. Option B, conjugate joints can form at different times in response to varying stress fields, right? And option C is conjugate joints are always shear fractures. It is not true. Does not need to have a always shear fractures. This is a conjugate joints do not relate to the orientation of principal stress. This is not. It does relate. We saw in this in this diagram that there is a relation between this conjugate joints and this stress field, right? So, and here if you see, if you look at this fracture planes or joint plane, the is sigma 2 is into this in screen, yeah. So option B is the correct options. So what happens if suppose you have a block, you have a stress field like this, sigma 1, sigma 3. So after a time what will happen is that there will be this formation of a conjugate shear fractures. Might be looking like this is the obtuse angle, but this is not. So you can see this is the joint plane, right? So it is related to the, if this is the case, if this becomes the obtuse angle, I'm sorry, so if this becomes the obtuse angle, the direction will change, right? So this will become the sigma 3, actually this is sigma 1 only, and this is, so this will be the acute angle, this will be the acute angle. Okay, so depending on the stress orientations, depending on the stress orientations, your shear plane will, the orientation of this conjugate shear fractures of shears, the conjugate joints will change. That is why it can form in any direction. Next question: which of the following statements about joint is true? Option A: joint can form in any type of rock regardless of its composition. Option B: systematic joints are irregularly spaced and oriented. Option C: joints are primarily formed under compressive stress conditions. D: open joints are always filled with mineral deposits. So it's asking which of this is the correct option. Think. So option A, okay, we'll look at one by one. So joint can form in any type of rock. It can, it is possible to form any type of rock, right? Regardless of its composition. Systematic joints are irregularly spaced, or no, it is regularly placed. It's not irregular. Joints are primarily formed under compressive stress conditions. It's not right. It's an extensive stress conditions. Right. Open joints are always filled with minerals. It's not true. It's not always. So it can form in any type of rock regardless of its composition. So it's not always true that it always filled with mineral deposits. We see a lot of joint sets in the field where they are open spaces, they are not filled with any minerals, right? And it is possible that joint sets forms, it's very possible that it forms in an extensional regime, these joint sets. So in the case of conjugate joints, it is forms under this compressive regime, but it is very much possible that you have this type of joints, these sorts of joints. So it can form in extensive stress condition as well. And irregularly spaced, no, it is always regularly spaced and oriented. Since it is saying systematic joints, systematic, so it's very systematic. So that is why option A is correct. Okay, let's move to the next question. What is the primary purpose of shear sense indicators in geological studies? Option A: to determine the mineral composition of rocks, to assess the age of rock formations, to infer the direction and nature of displacement during deformations, to identify the type of rock layers present. So what do you think? So it does not, it is not related anything about the compositions. We know the sense indicators, shear strength indicators, to gives us the movement directions, displacement directions during deformations, right? So to assess the age, it's nothing to do with this age, right? It is important for this direction and nature of displacement during deformation. So this is correct. Type of rocks, no, it is not related to type of rock. So this is wrong, this is wrong, this is wrong. So option C is correct. Okay, next question. Which of the following structures is considered a reliable shear indicators? sense indicator in ductile shear zones? Option A, slicken lines, asymmetric folds, fault gauge, boudinage. So remember, here we are asking, saying about ductile shear zone. So be careful. So we know slicken lines forms in brittle shear zone. Fault gauge is also part of brittle shear zone. We have been seeing, right? We have I have showed you a couple of more examples. And boudinage, we know it's also a part of brittle shear zone. And we know folding is a or part of or is a result of ductile deformation, where rock flows, not break, right? So this asymmetric folds, suppose you have this is or the best example of a asymmetric fold is second order folds, right? We have seen in the last lectures. So you can have, you know, like this, right? So these are asymmetric fold, and this gives you sense of movement. So this is a long, short, long. So this is a jet sapien, and this is S shape, and this is this jet sapien. Okay, let's move to the next question. In a shear zone, what does the presence of sigmoidal shear bands typically indicate? We have seen this in the very third question. That in shear zone, what does the presence of sigmoidal shear bands represents? Option A lack of significant deformation. Option B, the direction of shear and relative displacement. Option C, the age of the rock formation. Option D, the mineral compositions. So, no, I have not put it. So, we have seen in the initial slide. So, the sigmoidal shear bands. So, if you have so sigmoidal is like so suppose this is how it forms, right? This is sigmoidal. So you have, and just go back and show you those images. So you have seen this, right? So you saw this, right? This is how it forms a sigmoidal, and this gives the shearing direction. Right. This is where. So this gives you what? This direction of shear and relative displacements. It's nothing to do with age, mineral, or deformations. Okay, let's move to the next question. What type of shear sense indicator is formed by the deflection of pre-existing planar markers, such as veins, bedding layers within a shear zone? So, which or what type of shear indicator forms when you have a deflection of the pre-existing planar markers. So okay, I will go one by one. So pressure shadow is a result of deflection of pre-existing. It forms new, right? So you have a class and then you have shadow is forming, right? Pressure shadow. This is a formation of a pressure shadow. So it's not the correct. SC fabric is something, it's based on a continuous shearing. Suppose you have so due to the shearing this developed, and this continuous shearing, what will happen if you have something, then it will develop a new, you know, type of, so you will form like this. So S C, and then if you have further shearing, then you will find a later foliation plane, and which will be what, this C foliation will get rotated, and this will what will become, this will become somewhat parallel, and then there will be another foliation, and this will be C dash, so which will be we also called SC C dash foliation. So this is not a result of pre-existing markers, it forms new. Shear bands, it's not something that it's a bands of deformation, right? Shearing, so entire it's known as shear bands. This something is called drag force that forms due to the deflection of pre-existing markers. So I have just kept here one example to show you. So this is a normal drag, this is a reverse fault. So I will just draw the initial conditions. Initially it was or like this. Initially this was like this plane, this is a foliation plane. Then due to this stress condition or shearing, it got folded. But then what happens, the stress condition changed, and due to that a fold plane occurred, and then there is a slight movement, and this is a dextral movement. So due to this type of normal drag happens. So this is the drag which has occurred. So this can be normal, so this is a convex drag, this is a can be concave, and in the case of reverse it can be, this is something how it will form, and this is something how it will form in the case of convex. So drag or fold is the correct options. Let's move to the next question. Which statement about C dash type shear band is true? I just explained you one slides back. They are always parallel to the main foliation. They form at high angles to the main foliation during low strain condition. This indicates a significant reduction in strain within a shear zone. Option D. These are second generation of shear bands that form at oblique angles to the C bands. We saw right here. I just explained you. See here. So this becomes the C foliation. So I explained you, this is because of continuous shearing, and this is called C dash. This is, so this is an oblique to the main shear, and this is a later stage. So they are always parallel to the main. This is wrong, they are not parallel to the main foliation plane. They form at high angles to the main foliation during low. No, this is not a low strain condition, and this indicate a significant reduction in strength. This is also not a true. These are a second generation of shear bands. We saw that this is formed in the later stage. So second generation that forms oblique angle to the shear bands. So we saw that it's a forms at oblique in the shear bands. So option D is correct. Okay, what is an important consideration when interpreting apparent offsets in markers within a shear zone? Option A, the age of the markers. Option B, the orientation of the angles of the orientation and angle of the markers with respect to the shear plane must be assessed. Option C, only one marker should be analyzed for accuracy. Option D, the mineral composition does not affect interpretations. So when you interpret any offsets in markers within a shear zone, you have to take very important consideration. You have to understand that whatever you are observing, their orientations needs to be very sure about it, and the angles with the shear zone, angles of the markers with the shear zone boundary. And okay, so the age of the marker is, it's not important, it is not important that much. The orientation and angle is very important with respect to the shear plane, shear plane. So this is the correct options. Okay, look at the other options. Only one marker should be analyzed for accuracy purpose. You need to be, for accuracy purpose, it is important to verify our interpretations with more than one marker. So suppose you are seeing so there's a fault along this plane. So suppose you have a bed, another bed, another bed. So you are seeing these offsets, here, here, and this formation place has shifted. So this much offset, sorry, so this offset is getting recorded right here, this much. So we are not only seeing in one foliation plane, we are seeing in second foliation plane, in other foliation plane, and this is giving a direction that the fault has moved, in, so it has a dextral movement, right? And so this should be in this cross section you find some blocks, some porphyro, for example you find a sigmoidal porphyroclast. So from this you can see that this also giving a dextral sense. So like this, dextral shear sense, dextral shear. So this, with this and this, from both we are getting dextral shear sense. So this confirms that indeed we are seeing a dextral shear. So that's how we need to verify from more than one shear sense indicators. And the last is the mineral composition does not affect interpretations. Of course this does not affect our interpretation, especially when we are considering the markers. What does the Flint diagram primarily represents in terms of geological deformation? So now we have entered the last section of this question answer session, which is the Flint diagram. I hope you all have gone through these lectures and have learned through the Flynn diagram, or you have understanding of the Flynn diagram uh, from the structural geology courses. So what does Flynn diagram says, or why it is important? What does it represents, or primarily important for? Is it option A, the relationship between stress and strain? Option B, the stress ratio x by y versus y by z? Option C, the temperature distribution in metamorphic rock? Option D, the mineral composition of rocks? What do you think? We are very so we know that Flynn diagram is a, a representation of the ratio of this all these three axes. It's not related to the stress and strain, it's related to the strain. So it helps us to understand the 3D strain in the during the deformation of the rock deformations. So option B is correct. It's not about the temperature distribution, it's not about the mineral composition. So option B is correct. So we will see now this diagram. So this is the I've just kept here to help you understand. So this is a Flynn diagram, and we can see this y-axis is x by y, and z and the x-axis is y by z. And here, so this is represented as 1 plus e2, and this z is represented as 1 plus e3. You can represent it, right? And I'm not going to the details here, but I will help you to understand. So this is a case where k is equal to 0. And this in this x-axis where you have 0 y, right? You don't have, so y is 0, so this becomes k is equal to 0, and k is nothing else than this is a minus 1 by b minus 1. So this is a case of uniaxially oblate or pancake structures, and this is the area where we have plane strain. So oblate is, we can see here, this is oblate examples, oblate cake or uniaxially oblate pancake. So in this axis, in the case of plane strain, we have k is equal to 1 and volumetric strain is 0. There is no volumetric strain. So whatever you have, so it gets expanded in the other direction, extended in the other direction. And this y-axis where you have x is equal to 0, it is known as uniaxially prolate or cigar shaped. So this is how it deforms. Here we can see this cigar, right? It forms like this. So this is a cigar shaped or prolate, where k is equal to infinity. And here k is equal to 1 in the plane strain case, and this region between k is equal to 0 to k is equal to 1, we have general oblate or oblate fraction. We can say that field of flattening or general flattening, we also say. And from 1 to k is equal to 1 to k is equal to infinity, we have field of constriction or general prolate, where the k values slide between 1 to infinity. So this arrow, if you see this blue arrow, is so it's saying that is increase in the modeling difficulty in 2D. So it's difficult to understand in 2D way. So this helps you to understand. So we are going to solve a couple of more problems in this Flynn diagram on the basis of Flynn diagram concepts. So from here you need to be very sure. So here y is equal to 1, it is equal to 0. So here a is equal to b. So here what happening is a is remaining as this b. So this a and b is same. So let's try to solve some questions from here. In the context of Flynn diagram, what does a point plotted in the region between k greater than 1 so there is some issues with this question, I guess something. Okay, so I will just change this question. So here, okay, so field of flattening we know. Okay, I will just change this. Here I'm giving a condition when k greater than 0 and less than 1. So what will it represent? Pure shear conditions, contractional deformation, flattening deformation, or no significant deformation? Tell me. We learn. Okay, I will give you just hint. So I will draw the Flynn diagram for you. So this is x y y, this is y y z. Here k is equal to 0, k is equal to 1, here k is equal to infinity. So tell me, if this is the field, if I am talking about, this is the field I am talking about, so what would be the condition? In what does this indicates? You learned here, right? So this is a general oblate or field of flattening. So this is a case of flattening deformation, or a very specific, it will be general flattening deformation. So this is general flattening, and here we have, remember this is very important, general construction, right? Here we have plane strain, here we have a is equal to b, here we have k greater than 0, less than 1, here we have k greater than 1 and less than infinity. So these are the things you need to be very sure, you need to be very thorough about it. It will help you to understand and remember, understand the 3D deformation. So here you can see that here we have equal to the prototype bullet. Okay, we'll go to the next question. The parameter k in the Flynn diagram is defined as, the parameter k in the Flynn diagram is defined as a, the ratio of maximum to minimum principal strains, the ratio of shear stress to normal stress, the ratio of length to width of a deformed object, the ratio of x y y, where x and y are principal strains. We just discussed, so try to think about it. So we know, we just saw that k is equal to what? What did we see? Right? And what is a minus b? 1 minus x by y, 1 minus y by z. This is what we saw, right? Here. Sorry, I just wrote opposite. So it will be 1 minus. So what is this? So this is the ratio of minimum. So if you try to break this, so the ratio of maximum to minimum principal stress, no. The ratio of shear stress to normal stress, no. The ratio of the length to width of the deformed object, yes. This is the ratio between x and y, right? So here if you try to see this, if you try to see here, this here, so this k here, x y is equal to 1, so here x is equal to y. So this is the ratio of x by y, where x and y are the principal stresses. Okay, next question. Which line in the Flynn diagram separates the field of construction and flattening? So it's got repeated. I'm really sorry for that. So this is the same thing that is happening. So which line separates? Tell me. This is the line which separates, right? This is the construction, and this is the flattening. So what is this line? K is equal to 1, right? This is k is equal to 0. This is k is equal to infinity. So option is B. Okay, let's move to the next question. How does this Ramsey diagram differ from the Flynn diagram? So if you have seen the Ramsey diagram and Flynn diagram both, you will see there is a slight difference in these two diagrams. So this Ramsey diagram, what is this does is that it is the absolute values instead of ratios. It is a logarithmic diagram. So in this Flynn diagram, how does the Ramsey diagram differ from the? It represents. It is exclusively for the Brittle deformation analysis. No, it is not true. It represents only compressive stresses. No. It uses the absolute values instead of ratios. No. It plots logarithmic values of strain values. So what does that? It does is that this Ramsey uses the logarithmic values. So if you see here, here we do not use this ln values, but if you must have seen, if you have seen this Ramsey diagram, then they uses ln. hmm. What they uses? Ln x by y and ln y by z, and then how they define this k value. So option B is correct. Okay, this would be probably this. We have reached almost the last questions. In which scenario would you expect to find a Flynn diagram useful? So where will you find Flynn diagram useful? Option A, analyzing sedimentary rock layers for fossil content. Option B, evaluating the strain history during tectonic events. Option C, measuring the mineral hardness of the different rocks. Option D, determining the age of the rock formations. What do you think? No, it's not useful for sedimentary rock layers to fossil content. It is important for strain history during tectonic events. Option B. We saw that this this Flynn diagram is useful for understanding the strain. So once you have some deformed structures, from there you can get the strain, and once you have the strain, you can plot those strains in this Flynn diagram, and wherever with that point plotted, so that point will give you whether this is a case of flattening or constriction, whether it is a plane strain or oblate or prolate. So it is important for strain understanding, strain history during tectonic events. Option C is measuring the mineral hardness. No, it's not related to mineral hardness. Neither it is related to the age of rock formations. Okay. So question number, last question, I would say this is the last question. So in which scenario would you expect to find a Flynn diagram? Okay, so this is, I think, the repetitive of the question. So I will just go back to this Flynn diagram. I will ask you one basic questions that so if I ask you, if you have given like different geological, you know, features in, so what type of geological feature would you commonly analyze using this Flynn diagram? If you have fault zones or magma chambers, or you have shear zones, or you have sedimentary structures. So which features will be used commonly, or you will use to understand the strain history in this Flynn diagram? Fault zones, magma chambers, shear zones, or sedimentary structures? What do you think? Magma chamber is, no, this is not important. Shear fault zone is a part of brittle deformation. So this will not generally study strain. Shear zone is something where we get all this strain ellipsoid, and we have a lot of strain, high strain, and we use these shear zones features and plot the strain ellipsoid in this Flynn diagram and help us to understand the strain history. Sedimentary structure is not, so shear zone is important to understand. Okay, if I ask you that how does this Flynn diagram refers to the shape of ellipsoid, how does the Flynn diagram relate to the shape of the strain? So it is related to the strain ellipsoid. So here we have oblate. We know that here we have oblate ellipsoid. So I have not kept one image where you can visualize through strain ellipsoid. So you can also understand or visualize this Flynn diagram deformation through strain ellipsoid. So Flynn diagram this okay, so here this oblate or here this general oblate ellipsoid, or if you reach to plane strain, we have very the prolet becomes equal to oblate. So here we have plane strain ellipsoid, we have equal to the A is equal to B. And if you come to this region, we have general prolet or the construction ellipsoid. And once you move to this K is equal to infinity, we have the pure prolet ellipsoid. So here the ellipsoids will something look like, like this. And if you talk about here, it will look like this. The 3D ellipsoid. Okay, if one last question, if I ask you, so what is the difference between Mohr diagram versus Flynn diagram? What will you say? You have studied Mohr diagram. So here, this Mohr Flynn diagram, we know it gives us the only the shape of ellipsoid. It does not talk about the amount of strain, right? We here we discuss what the ratio of strain, right? So it only talks about the ratios value. It does not about the amount. So it does not talk about amount of strain. Here it mostly deal with magnitude of strain or the shear stresses, right? It does not talk about the shape of ellipsoid. Right. So it is very important to understand the Moore diagram and Flynn diagram. And one more important thing is that Flynn diagram assumes what? That volume change during deformation is so volume change during deformation is negligible, or in other way you can say that it assumes volume constant deformations. So this is if we limitations of Flynn diagram, right? But this is not the case. There is not always the volume constant deformation occurs. There is many cases we see that there is a volume change in the deformations. And the best part is that it simplifies this 3D strain into 2D representation. And usually it does not capture the entire strain of the 3D. And it is the data which we put here, the whatever values we are getting here, it depends on the input that we apply, right? So it's very important that what accuracy which we are input, we're giving the input. So if we are measuring incorrect data, it will lead us to, it will give us improper strain ellipsoid. And we know that we learned that this Flynn diagram is only majorly used for shear deformations. It is very limited use in case of brittle deformations. So these are some of the limitations that is there with this Flynn diagram. So with this, we have come to the end of this week 4 live interaction sessions. So I would recommend you all to go through the lectures if you have not been, and try to watch, interact. If you have any further questions, you can always uh, write in the forum, discussion forum, and I will be happy to interact there with you all. And I had really good time uh, with you during this live sessions all this 4 week. And so this is the last week which we had today. And yeah, so there is now time to say goodbye to all, and we'll see you in future. Okay, thank you so much for joining us, joining for this live interaction sessions continuously for the 4 weeks. And I hope you have enjoyed this live interaction session. So if you have any future questions, as I said, please write in the discussion forum, and I will be happy to answer. Thank you so much. Bye.